All right, here's Avogadro. So what's Avogadro's number?
6.022.
Yeah, 6.022 times
10 to the 23rd.
10 to the 23rd. And so this is a number you'll need to memorize. Or where did Avogadro's number come from?
It's from carbon 12.
Yeah, it's a number of carbon-12 atoms. So how could you count that many? You know, that's like 602 billion trillion. Could you count those? So how was it determined? Who counted those? And so actually, they weren't counted individually. It was just using some stuff to figure out how many it contains. So French scientist Turn made the first accurate measurement of Avogadro constant. That is Avogadro's number, finding that a mole of hydrogen consists of 7 times 10 to the 23rd molecules. With this off a little bit, the modern measured value is 6.0 times 10 to the 23rd molecules. So it's pretty good, correct order of magnitude. There are other ways to determine it. You don't literally count them. You figure out things like this for some reason. And so once we have that, then we can convert conversion factor. Avogadro's conversion factor here. Here they're using 3 sig figs. We're going to use 4 sig figs, 6.022. But here we can convert moles into atoms. And we have other conversion factors as well. So we'll be taking a look at these conversion factors that were written up there earlier. Okay, so let's skip this. Okay, we talked about the molar mass. Ready? Okay, so here's some molar masses. So this balloon here is about 1 mole of nitrogen, N2. A mole of nitrogen weighs 28.02 grams. The average nitrogen weighs 14.01 mole. It doesn't look like it, but that would be about 25 liters. Here's a mole of iron. Now, if I look at the average mass of an iron atom, it's 55.85 U per atom. But if I have a mole of atoms, it will weigh 55.85 grams. So all we do is weigh out 55.85 grams of iron, and then we know that contains 6.022 times 10 to the 23rd iron atoms. Here's a mole of aluminum, which is 26.98. These are off the periodic table, so these are the average. Mercury is 200.6. This would be 200.6 grams of mercury. Sodium is 22.99 grams per mole, or U per atom. Copper is 63.55. And so these are just the atomic masses and molar masses here. This is copper. We call this copper 2. Copper can be copper 1 or copper 2. And that's sulfate's -2, so that's going to make copper 2. This is copper 2 sulfate, pentahydrate, or .5 hydrate. It's blue like this. This is mercury 2 oxide. This is a mole. This is going to be a mole of water. A mole of water weighs 18 grams, so it's 18 milliliters. This is a mole of oxalic acid. This is a different way of writing oxalic acid. What's the way we write oxalic acid? The way we write oxalic acid is H2C2O2. Here's oxalic acid dihydrate, which is going to weigh a little more. And so that's a mole. So the reason the mole is chosen like this is because a mole is about visible macroscopically, whereas a dozen would not be visible. Even a billion would not be visible. And so we need a huge number, like a mole. And so we could have 1 mole, 2 moles, double it, etc. So these are some conversion factor problems here. We'll take a look at in a little bit. This brings us to stoichiometry. Stoichiometry is just quantity relationships. And quantity relationships are just these converted factors. And so we can go from things like mass to moles, and the moles to numbers. That's what we did over here, but I erased it. We went from, we went from quantity. We went backwards here. We went from 9 billion water molecules, then we converted it to moles of water molecules, and then we converted it to grams. So this is called a stoichiometry map, and this is a very common conversion. A very common conversion would be grams to moles, or moles to grams, using the mole amounts, or it'd be moles to number, or number to moles, using Avogadro's. This is an abbreviation for Avogadro's number, NCA. Avogadro's constant, or Avogadro's number. So, this is just a general one. It's not specific. It's just a measured quantity. And so the measured quantity could be milliliters, grams, whatever. So here's a specific application. So an example of this would be how many molecules are in 454 grams of water. So we're just going to go backwards in this case. They give us a conversion factor. 454 grams is equal to 1 pound. But I don't know if we need that. So, in other words, this is how many molecules are in about 1 pound of water, 454 grams. And so it's just conversion factors again. We start off with 454 grams of H2O. And then the conversion factors that we're going to need are things like this. One is the average water molecule weighs 18.02 U per H2O molecule, or 18.02 grams of H2O per mole of H2O molecules. So we could use this one as is or flip it upside down. In this case, we're going to flip this one upside down and get grams of water on the bottom. And so we'll have 1 mole of H2O molecule is equivalent to 18.02 grams of H2O. All right, but a mole is a little bit abstract. You know, it's a big number. Let's see how many moles that would be. So 454 divided by 1802. So 454 divided by 1802 gives us 25.194 moles. 25.194 moles of water. So you have about 25 moles of water. Well, how much is 25 moles of water? Well, if we go back to the previous page here, in the previous page, one more. That's it. Here. If this is 1 mole of water, we'll have 25 of these. So that gives us how many moles of water we have. But they don't want moles of water, they want to know how many water molecules there are. And so we're going to use Avogadro's number for this. And that is there's 6.022 times 10 to the 23rd H2O molecules in a mole, 1 mole of water. And so using dimensional analysis, we'll see that the grams of water cancel. That leaves us with moles of water. Moles of water cancel, and that leaves us with H2O molecules. It's going to be 25 times Avogadro's number. So that comes up to times 6.022 times 10 to the 23rd equals and it gives us 1.51. Now we're allowed 3 sig figs here, so I'm going to carry 1 extra. So 1.517 times 10 to the 25th H2O molecules. This is a huge number, and so how big is this number? So we'll carry it over.
25 places. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So that's 1,000 million, billion, trillion, 1,000 million, billion, trillion. And so this comes out to 15.1 trillion. Water molecules. Actually 15.2, I need to round it out. 15.2 trillion water molecules. Let's see. Two ways you can check the answer. One way is you could do what we were talking about, Gabriel mentioned about ballpark. Ballpark check. Ballpark check means call it 500 divided by 20. 500 divided by 20 would be about 250. What would it be? 25 would be about 25 times about 5 would be about 125. So times 10 to the 23rd. 125 times 10 to the 23rd. You can move the decimal over. So I got 150. So ballpark is right. Or we can check it against the answer in the book. Let's see if we can pass it. What they got was this 1.5 times 10 to the 25. They got the wrong number of 6 figs. How did they get the wrong number of 6 figs? Oh, no, they didn't. This is their ballpark check there. Their ballpark check was better than mine. They got 1.52 times the 25th. That's what we got. 1.52 times the Okay, the next thing is this 7-6. So we'll come back and look at some problems. Let me cover the topics in the chapter first. Come back and look at problems. We have different ways we can express composition. Let's look at H2O, an example here. If I look at the composition of H2O, I'm going to look at it percent by atom, which we'll put in parentheses like this. Percent by atom, what percentage of H2O is hydrogen? Well, I look, how many hydrogen atoms do I have? I have 2 H atoms. Out of a total of how many atoms? 3 atoms total. Times 100%. So this is going to give us I'll just do this. We could do this exactly because it's exact. But I'm going to just round it. We're just going to say 67, 2/3, 67% hydrogen. And so this is the percent hydrogen by atom. How about oxygen? Well, the rest is oxygen. So if it's 67% hydrogen, it's got to be 33% oxygen because it's got to add up to 100%. Or I can calculate it. It's 1/3 oxygen, 2/3 hydrogen. If I do percent by mole, I'll get the same thing. In this case, if I had a mole of water molecule, how many moles of hydrogen do I have? So let's say if I had a dozen water molecules, I'd have 2 dozen hydrogen. If I had a mole of water molecules, I'd have 2 moles of hydrogen. And so in this case, I'm going to get 2 moles of H atoms divided by 3 moles of total atoms. So if I have 3 moles of atoms, 1 mole of water is going to have 3 moles of atoms total, times 100%. And so I'm going to get the same thing, 67% by mole. We'll put this in parentheses for H, 33% by mole O. And so atom percent and mole percent are the same thing. Rather than dealing with individual atoms, we're dealing with moles of atoms. But it's going to be the same ratio. This is different than a mass percent. And so if I look at a percent by mass, it's a bit different. First off, the total mass of water, I have 2 hydrogens at 2.02, and 1 oxygen. So this is 2 times 101, which is 202, and then 1 times 16.00, which is going to give us 16.00, and so it's going to weigh 18.02. I can do this either in grams per mole or U per molecule. It's the same number. And so oftentimes we leave off the units because units are going to depend on what we want, grams or U. And so if we do the percent by mass hydrogen, then I need to know how many grams of hydrogen. Well, I have 2.02. This is going to be 2.02 grams per mole of hydrogen divided by 18.02 grams per mole of water times 100%. And so let's figure that out here. I'm going to get 2.02 divided by 18.02 times 100. Yeah. How many sig figs? Now, if I look at this, I'm only going to get how many sig figs here? I'm only going to get 3 sig figs. Actually, I don't want 3. I want 4 sig figs. How can I get 4 sig figs? How I can get 4 sig figs is I shouldn't have used 101 here. In most cases, using 101 is fine, like here. If I use 101 here, then I get 202, which gives me 202 plus 16 gives me 1802, and that's how many sig figs? That's 4 sig figs. I shouldn't have used 202 here. Instead, what I should do is I should use 2 times 1.008. If I use 2 times 1.008 grams per mole, then I'll get 4 sig figs. And so instead of using this, I'm going to use 2.016 grams per mole of hydrogen rather than 2.02. And that will give me 4 sig figs. So this is why I wrote 2 masses for hydrogen. It depends, normally we want a certain number of sig figs. And so in this case, I'm going to do 2.016 divided by 18.02. And actually, I didn't write that earlier. I'm going to get 11.187% hydrogen by mass. Earlier, versus 2.02 divided by 18.02, I got 11.098. And so hydrogen is going to come out to 11.19%. Hydrogen. So water contains 11.19% hydrogen by mass. But how much oxygen is it going to contain? Well, the rest is oxygen, so it's going to be 88.81% oxygen by mass. And that's going to add up to 100%. Or we could just do the calculation. If we did the calculation, it would be 16 divided by 1802 times 100, which would give us 88.81%. So why is it, when I look at the atom or mole percent, it's mostly hydrogen? But when I look at the mass, it's mostly oxygen. Why is that?
Oxygen base.
Yeah, oxygen is a lot heavier. Oxygen is 16 times heavier than hydrogen. And therefore, that's why the mass percent is 75. So when we're looking at the composition, you know, everybody knows the composition of water. What is the composition of water? It's H2O. But does everybody know the mass composition of water? Did you know? No. The mass composition is 11% hydrogen, 89% oxygen. That's the mass percent. And so another way of writing the composition is like this. This would result in 11 parts of hydrogen, 89 parts of oxygen. Have you ever seen water written like this? Water's never written like this because formulas never do it based on mass. This is based on mass. We never do that. And so there were some mass problems. You know, you had this many grams of sulfur, this many grams of oxygen. It's kind of foreign thinking about that because normally when we think about sulfur and oxygen, we need to know the atom ratio. I want the atom ratio, not the mass ratio. That was one of the homework problems earlier. So this is kind of weird to represent the composition in terms of mass, but mass is, you know, so familiar. Sometimes we need to know the mass. So ammonium nitrate, we know the atom composition of ammonium nitrate. It's NH4NO3, ammonium nitrate. But, you know, when you go and buy ammonium nitrate, you want to know how much nitrogen you're getting because nitrogen is the active ingredient. So the more nitrogen, the better. So if I buy a pound of ammonium nitrate, you know, how much nitrogen are you getting? And so maybe let's not do pounds, let's do a kilogram, so about 2 pounds. And so a kilogram of ammonium nitrate contains how many kilograms of nitrogen? When I ask how many kilograms, should I write N2 or should I write N there? And it turns out I'm going to write N because I'm not asking how many kilograms of nitrogen gas are in ammonium nitrate. There's no nitrogen gas in ammonium nitrate. There are nitrogen atoms. One nitrogen is in ammonium, the other nitrogen is in nitrate. But there's no N2 gas. And so here, when we're talking about nitrogen, we're talking about atomic nitrogen. So there are 2 ways I can do this. One way is I can calculate the percent by mass nitrogen and use it as conversion factor. The other way is I can just use dimensional analysis and not even bother calculating the percent by mass nitrogen. But let's say we're looking at different brands of fertilizer and we want the fertilizer with the highest nitrogen content. Well, usually they sell this by the pound or they sell it by the kilogram. You know, and when you go buy it, they don't sell it by the atoms or molecules. So when you go buy some fertilizer, you're going to buy 50 pounds of fertilizer. And so in that case, percent by mass would be more useful than percent. And so let's say we had some pure ammonium nitrate. What is the mass percent of nitrogen? So the first example is the percent by mass of nitrogen. in ammonium nitrate. The percent of mass of nitrogen is going to equal the grams of nitrogen. Again, this is atomic nitrogen per grams of total times 100%. And so we're trying to figure out, well, how many grams of nitrogen are there per total grams of ammonium nitrate? So the first thing is we can figure out the grams of nitrogen. The grams of nitrogen is there are 2 moles of nitrogen atoms here. And each mole of nitrogen weighs 14.01 grams. And so that's going to give us 28.02 grams of N, nitrogen atoms, or moles of nitrogen atoms, divided by the total mass. The total mass is, we'll have to calculate it. Actually, I calculated it earlier. Do you remember what the total mass was? It was 80. I made the mistake. I called it 70. 80.06 grams of ammonium nitrate, which would be the total. Okay, so this is going to be divided by 80.06, and then we want to convert it into percentage. To convert it into percentage, we just multiply by 100%. Times 100%. And so this is 28.02 grams of nitrogen atoms divided by 80.06 grams of ammonium nitrate times 100. And we're allowed 4 sig figs, so it just comes out to 34.998. 34.998% nitrogen by mass, or 30. We're going to round this up. 35.00% nitrogen by mass. So for every 100 grams of ammonium nitrate, I get 35 grams of nitrogen. So for every kilogram, I'm going to get 0.35 kilograms of nitrogen. And so the first way I could do this is I could just go 1 kilogram of ammonium nitrate. And this is a percent by mass, so we can use whatever units we want. So this could be kilograms, pounds, whatever. And so what I could say is that I'm going to have 35.00 kilograms of nitrogen for every 100 kilograms of ammonium nitrate. And so this is going to give me 0.35. And I'm allowed how many sig figs? Well, it depends on how many figs I'm looking at. So 0.35 kilograms of nitrogen. Or I could use dimensional analysis. If I use dimensional analysis, this is the way I do it. I'd start off with 1 kilogram of ammonium nitrate. And then I'd convert that to grams. And so there are 1,000 grams per kilogram. And that gives me grams of ammonium nitrate. And then I'm going to use the molar mass. The molar mass is 1 mole of ammonium nitrate weighs 80.06 grams of ammonium nitrate. Okay, so kilograms of ammonium nitrate cancel, grams of ammonium nitrate cancel. That leaves us with moles of ammonium nitrate. Once I'm at moles of ammonium nitrate, then I'm going to use the formula. For every 1 mole of ammonium nitrate, I have 2 moles of nitrogen. So I have 2 moles of nitrogen, N atoms, for every 1 mole of ammonium nitrate. And that just comes from the formula. This is from the formula. There are 2 nitrogens for every ammonium nitrate. And then I know the average mass of nitrogen. The average mass of nitrogen is 14.01. And so I could say there are 14.01 grams of nitrogen for every 1 mole of nitrogen atoms. And so moles of nitrogen cancels, moles of ammonium nitrate cancel. That leaves us with grams of nitrogen. And then I need kilograms. And so I'm going to convert it to kilograms, 1,000 grams per kilogram. And so this 1,000 cancels as well. Okay, so when we go ahead and calculate that, I get 2 times 1401 is 2802 divided by 80.06, and I get 0.35 kilograms of nitrogen. So here I didn't have to calculate the percent nitrogen mass. I just used dimensional analysis. And typically we just use dimensional analysis, even though it looks like it takes up more steps. This one takes up a lot of steps too, because we have to calculate the percentage.
What does that say back over there? Mass of nitrogen and what? Looks like a
Here, and use as conversion factor. So
Oh,
first
okay.
calculate the percent by mass nitrogen and then use it, and then use as a conversion factor. And so we first calculated percent by mass nitrogen and then used it as a conversion factor. Here it's 35 parts out of 100. Units. So here's an example of where we want to know the mass. We want to know the masses because we buy fertilizer by the pound. Or the
NPA
kilogram.
is what again?
Dimensional analysis. So if we have the chemical formula, like ammonium nitrate, then we can tell a lot, about it. But where does the formula come from? Who figured out what the formula for ammonium nitrate is? Well, I guess you could figure it out because if you know the composition of ammonium and you know the composition of nitrate, you could figure out the composition of ammonium nitrate. So we're going to go on to 7.7 here. So where do formulas come from? In other words, where does the composition come from? So let's say we have an unknown pure substance. If we have an unknown pure substance, we send it out for chemical analysis. When they report the results to you from the chemical analysis, you have to pay money and they'll analyze it. But when they report the results, they usually report the results in either grams of each element, in a given sample. So you might give them like a 10-gram sample, and then they'll tell you how many grams of this, how many grams of that, how many grams of that are in the 10-gram sample, or a 100-gram sample. So grams of each element in a given sample, or percent of each element in the sample. So if we're given either of these two, then what we can do is we can figure out something called the empirical formula. The empirical formula is going to be the simplest. mole or atom ratio. A formula is a mole or atom ratio. And so the simplest mole / atom ratio. And then sometimes what we'll do is we'll go on another step. If it forms molecules, so if it forms molecules, then we can get the molecular formula. And we need additional piece of information. We have to send it, and we need to know how much a molecule weighs. How much a molecule weighs is called the molecular mass. And so if we have the molecular mass, then we can get the molecular formula. But oftentimes we'll just stop at the empirical formula because a lot of things don't form molecules. And so that extra step isn't always necessary to do. So let's do an example of this. Here are the steps in determining the empirical formula. Step 1, determine the percentage composition by mass, or the mass of each element in a sample. So that's typically what we get. To determine that, you send it out and you pay somebody money, and then that's what they're going to give you. They're going to give you the report from there. Step 2, convert the masses into moles. Step 3, get the mole ratio. Step 4, get the simplest mole ratio. Step 5, round it. And so let's take a look at this compound here. Well, maybe we'll do one from the back. Do one from the back. Yeah, I'll do something like this. 60. A compound is found to contain 39.12% carbon. So if you send out a sample, it comes back from analysis, and it came back in terms of percent. Sometimes it doesn't. Sometimes it comes back in terms of this. You know, you have 16.99 grams of sample, and in that 16.99 grams, they found 11.89 grams of iron. So we can calculate the percent iron here. 1189 divided by 1699 times 100. So that gives you the percent iron. But typically we'll get this. You know, either we'll have to figure out the percentage or we'll get the percentage. But once we have the percentage, then this is what we'll do. Get the empirical formula. So we're doing 39.12% carbon. That's what came back from analysis. This is by mass. 8.772% hydrogen. 52.11% oxygen. Okay, does this add up to 100%? See. If it adds up to 100%, then I'm not missing anything. Let's see if it adds up to 100%. So 39.12 plus 8.772 plus 52.11. You know what it adds up to? 100.002%. This has too much of something. What do you think that's due to? Rounding. So, all right, it adds up. Close enough. Okay, so the first step is we assume 100 grams. If we assume it's 100 grams, how many grams of carbon are there? 39.12 grams of carbon, 8.772 grams of hydrogen, 52.11 grams of oxygen. And then we convert to moles. Convert to moles. So to convert this to moles, we know that 1 mole of carbon on average weighs 12.01 grams. And so that's going to give us what? So I'll take 39.12 divided by 12.01. Gives me 3.257. I'm allowed 4 sig figs, so I'm going to carry 1 extra. 3.2572 moles of carbon. And then hydrogen, this is not H2, this is just H. Because we're going to have hydrogen atoms in this, and H2 would be hydrogen gas molecule. So I want 4 sig figs, so I'm going to do 1 mole of H weighs 1.008 grams. I'm not going to use 101 because I'm not adding it to anything, so I want to get at least 4 sig figs here. So this is going to be 8.772 divided by 1.008. And that gives me 8.702 sub 3 moles of H. And then oxygen, 1 mole of oxygen, the average oxygen atoms weighs 16.00 grams. And so I'll get 52.11 divided by 16. And that gives me 3.256, and then carry 1 extra, 8 moles of oxygen. Now, a formula is the molar atom ratio. So formula equals mole or atom ratio. And so the formula for this compound here that I have is this. I have C 3.2572, H 8.7023, O 3.2568. But it's not so simple, is it? So we need to simplify this and clean it up. This looks awful. So what should I do? Should I round it? C3H9O3? C3H9O3? Now that's overzealous. The rounding's a bit too much. This is 3 1/4. This is 8.7, 3 1/4. This is overly zealous in terms of rounding. So I'm not going to do that. What we do is we have a little trick. The next step is to divide by the smallest. Divide by the smallest number of moles. So which one's the smallest? Looks like this one is the smallest, right? And so I'm going to do this. I'm going to take 3.2572 and divide it by 3.2568. And then hydrogen, I'm going to take 8.7023 and divide it by 3.2568. And then oxygen will be 3.2568 divided by 3.2568. All right, so the first one is carbon. Let's do that. So let me do that with the number of digits I have. 3.2572 divided by 3.2568. and I get carbon, log 4 sig figs. So I get carbon 1.000, and then I'll carry one extra, 1. Then hydrogen, I'll do 8.702. 8.702 divided by 3.2568. And then I get hydrogen at 2.6719. And then I have oxygen at 1.000. But formulas are simple whole number ratios. Do I have whole numbers here? No. I don't have whole numbers. You know, this, when I look at this, this is about 2 2/3. I don't want to round that to 3. I think that would lead to a pretty big rounding error. And so if it's 2 2/3, then this is what I'm going to do. I'm going to, 2 is, what is 2? Unless I made a mistake. Did I make a mistake? I think I made a mistake. 2 is 6/3. So 6 plus 6/3 plus 2/3 gives me 8/3. 8/3. Roughly. So if I multiply this by 3, that might simplify it. And so I'm going to multiply by 3 times 3 in this case. Sometimes I'll double it. And so this is what we end up with here. If I get 1.5, then I'm going to multiply by 2, because 1.5 will turn into 3. If I have 1 1/3, or 1.3, then I'll multiply by 3. If I have about 1.67, which is 1 2/3, which is 1.33, I'll multiply by 3 as well. And so this is pretty close to 2 2/3, about 8/3, so I'm going to multiply this whole thing by 3. So this is going to be carbon 3.0003, hydrogen, so let's see what that comes out to, times 3, and I'm going to get 8.0158. So hydrogen 8.0158 and oxygen 3.000. All right, well, should I multiply this one to try to get it a whole number? No. You know, this is close enough to 8. And so what we're going to do is we're just going to call this C3H8O3. C3H8O3. That would be the formula there. And so here, I'm okay. I'll just round that to 8. That's close enough. Here, I don't want to round that to 3, you know, because it's a little bit far off from 3. Does that make sense? All right, why don't you try one of these? Here. Why don't you try number 61? See what you get.